Hello everyone, I'm Li Xian. Today I will introduce our work. WidePipe high-throughput deep learning inference system on a cluster of neural processing units. Deep learning has been widely applied in many fields, including natural language processing, computer vision, autonomous driving, and speech recognition. It challenges to design an inference system that corresponds to diverse and highly concurrent requests on an NPU-based cluster, which promotes to inference system must have the ability to elastically deploy heterogeneous model servings. The NPU-based cluster is a practical architecture which leads to the multi-tailed scheduling. This multi-tailed scheduling corresponds to the multi-level parallelism. Multi-chips corresponds to the request parallelism. Multiprocessor corresponds to the serving parallelism. And the multi-core corresponds to the operator parallelism. The core is the minimum granularity of resource allocation. We use a bottom-to-up approach to coordinate multi-level scheduling, which can fully tap NPU computing power. There are two motivations for our work. From Figure 1, we can see that the sensitivity of resource usage from different models is different. For AlexNet, the latency hardly changes when the resource beyond 8 cores. For ResNet 15, the more resource allocated, the lower the latency. Therefore, we need to adopt an adaptive core granularity allocation and device co-location. However, we find that the different configuration of serving leads to different co-location overhead. From Figure 2, we can see that the type of neural network and the size of the allocated resource both affect the inference latency. This inspires us to adapt an adaptive serving configuration based on NPU runtime status. Now we show a case to study the benefits that can be obtained. The first point, through fine-grained best cost-effective resource allocation, is prolong the latency of the yellow and the green model serving. But more serving can be deployed with the saved computing resource. This way avoids the wait time of blue and red serving. In addition, adaptive resource allocation can be further benefits. For example, reducing a core of green serving and add to the yellow serving that can bring greater benefit. The blue serving and the red serving can also take the same approach to increase benefits. The WidePipe using reinforced learning to autonomic tuning multi-parallelism for large batch size requests. The state of our agent includes free course of the current device and the ID of the job that can be scheduled. The action of our agent includes the allocated core number, batch size, and the ID of the current device. The reward of our agent includes CEFF and COO, which are used to evaluate the resource utilization, cost performance, and the core allocation overhead. The scheduling controller deployments the model serving according to the device of our agent. We implement WidePipe to manage machine learning serving based on Kubernetes. Our environment has 250 nodes. Each node has 4 NPU and each NPU contains 32 CUS. We use the embedded dataset as a request and created a request stream as follows. Figure 4 shows the throughput of different scheduling methods in a cluster with 1000 NPUs. WidePipe's throughput was 2.11 times and 1.11 times that of TensorFlow serving and the core-based scheduling. We can also see that the only setting CEFF or COO for reward function will not bring good benefits. From Figure 5, the latency overhead of WidePipe was no more than 90% that of TensorFlow serving, and the average latency is within 100 milliseconds. From Figure 6, the throughput of the WidePipe increased linearly as the number of nodes increased. Its throughput at 1000 nodes is 8.8 times that of 100 nodes. That's all my presentation. Thanks for your attention.